For this lecture, we're going to continue the discussion of an introduction to waves. So we haven't gotten to electromagnetic waves yet. We're still talking just about physical waves. Where I left off was that the second derivative of the function f, which describes the shape of the wave, anyway, that derivative with respect to space is equal to 1 over the velocity of the wave squared, and the second derivative with respect to time. So if we had a wave which then moved this way and moved its position by a length vt, then we would basically take our original wave and rewrite it. Actually, we rewrote it as a function g, where z minus vt. Now, the wave could move in the other direction, in a minus z direction, the minus z direction, which would then make a waveform over here. And so it's now traveled a distance minus vt. And so in that case, our function would be, I'll call it h, z plus vt. So if we want to consider all possibilities, then I can have a wave which is a combination of right traveling waves or left traveling waves. And so since waves interfere with each other, then I can break down my waveform into left traveling waves and right traveling waves. Okay, so let's consider now sinusoidal waves. So in the most general form, I can write this wave, I can draw this wave like this. This is z. This is the amplitude, like this. So the parts of the wave, which you're probably pretty familiar with, this is the wavelength, basically the distance of one cycle of the wave. This is the amplitude, which we'll call a. The wave doesn't necessarily have to start at 0, and so I can make an offset right here, which I'm going to call, for the time being, delta divided by k. That's that distance here. So the mathematical function for this wave is the amplitude times the cosine times k z minus vt, that's the position, plus an offset delta. So basically, yeah, a is the amplitude. It's the height, the maximum height of the wave. K is the wave number. Lambda is the wavelength, which I can write down as basically how many wave numbers there are in 2 pi radians. Basically one cycle is 2 pi. Delta is the phase, by how much I'm shifting, how many radians I'm shifting my wave from being centered at the origin. T is the period, so the time for one oscillation, which if I think about it, one oscillation, the length is lambda, the speed is v, and so therefore I can write the period as 2 pi over the wave number times v. F is the frequency, so it's the number of oscillations in a period, or for one period it would be one oscillation. So that would be 1 over the period, which I can now flip over and call kv over 2 pi. or v over lambda, depending on how you want to write it. But if I write it that way, that means if I multiply both sides by the wavelength, that means the speed of the wave is equal to the frequency times the wavelength. So that's a good equation to remember. Is you want to remember that the speed of the wave is equal to its frequency times its wavelength. Now if I consider an angular frequency, so 2 pi times the linear frequency, then I would get basically 2 pi over the period. And let's see, 2 pi over the period would be 2 pi over 2 pi over kV, or kV. So I could write the angular frequency then as the wave number times the velocity, or I could rewrite this as the velocity is omega divided by k. So I can either write it in linear terms or angular terms. However I want to write frequency, it's still the velocity of the wave is equal to something related to wavelength and something related to frequency. Okay, so now I can put all this together. If I put in the v to my equation, I would have f is equal to the amplitude times the cosine of k times z minus omega t plus my phase. Now this is for a wave that's traveling to the right. Before we said we could have a wave traveling to the left, but that would mean I would have to use a negative velocity. So this one is for the right. This would be a wave traveling to the left. Like so. Now, the interesting thing is that the cosine is an even function, so the cosine of a negative is equal just to the cosine of that angle. So in this case, I could actually take out the minus sign, and for my left-going wave, I could have minus kz minus omega t plus a positive phase. So if I want to think about it in terms of a positive phase, you know, for a right-going, everything is the same except for the kz. In this case, the kz is negative. So this may be an easier equation to remember, that a left-going wave has a minus kz, a right-going wave has a positive kz. Okay. Now, we can also write our waves in terms of complex notation, because if you remember, e to the I theta is equal to cosine theta plus I sine theta. So that would mean that the cosine part is the real part. So I could write down my wave function as the real part of a e to the I kz minus omega t plus the phase. So in that case, if I really wanted to generalize, I could write down the complex form of the wave function as will allow the amplitude to be complex, and this would be e to the I kz minus omega t. Where in this case I made the amplitude complex by saying the real amplitude times e to the I times the phase. The phase is just a constant number, so I'll lump that in with the amplitude and make a tilde a times e to the I times the phase. And which means that the wave function is the real part of my complex wave function. Okay. And so I mean, as a short note, Griffith's book used the tilde for the complex function. So we're going to follow along with that notation, even though other textbooks may use a different notation for the complex numbers, or sorry, complex functions. Everything that we do in this class will be with the tilde symbol. Okay. So now that we've written everything, now that we've kind of generalized our wave function into a complex wave function, that means that any wave function we have can be broken down into a Fourier analysis. So we could write down our complicated wave equation as the integral from minus infinity to infinity of the amplitude in the wave number space times e to the I kz minus omega t integrating over the wave space. Okay, and so what's the advantage of that? Well, the advantage now is if we can break it down into a Fourier transform, that means that we can write every one of our wave as a linear combination of sines and cosines. So now we don't have to necessarily worry about whether or not our wave is just a pulse or if our wave is some weird shape. We can just consider now that the simplest form of our wave being, so now we can consider our wave to be a nice clean sinusoidal function.